Hey guys, thanks for turning on this video, and I'm going to try and help you understand some more things about determinants. We have an exam coming up, and I just thought it might be nice to have a chance to talk to you before we have class on Monday, so that you can start to kind of get on top of the material now. We started talking about determinants in class, and I gave you basically a procedure for finding the determinant of a 1x1, 2x2, and 3x3 matrix. And then we started talking about larger matrices, and what we saw was that we have to use a little bit more convoluted procedure to find the determinant of a 4x4 or larger matrix. So I thought we would start this video with just a practice example, and then I'm going to just go through a few more of my notes so that you can kind of get a little bit more of a jump start. It's just a few pages of these notes here, just to get a little more of a jump start on chapter 3. Okay, so here's an example. Here's a 3x3 matrix, and let's say we want to find the determinant. I actually say find the determinant by using two methods, and that's because with a 3x3 matrix, we can choose to just use the arrow method. Let me remind you, the arrow method is where we just recopy the first two columns to the right of the original matrix. And then we just calculate 6 arrows here. The first 3 go diagonally down to the right, and then the last 3, which get subtracted, go up and to the right, something like that. So let's just see what we would get using the arrow method. That's the sort of the method number 1. The arrow method here. So we would get the determinant of, let's call this matrix A. Okay, so the determinant, let's see, the first diagonal, 2 times 1 times 0, that would be 0. And then negative 3 times negative 4, that's positive 36. The next term is negative 5 times 1 times 1, that would be negative 5. We're adding negative 5, right? Then we go the other way, and we subtract the diagonal up this way, negative 4 times 1 times negative 5, that's minus 20. And the next diagonal is 1 times 3 times 2, which is 6, so we subtract 6. And then the last one has a 0 in it, so that's just going to be 0. So we can calculate all of this. It's just 6. This is really going to be minus 5 and minus 20, so that's 11 minus 6, which is an answer of 5. Okay? Now the other way to do this, I'm going to rewrite my matrix over here again. The other way to do this is to use cofactor expansion, right? I explained it to you guys as a way of finding the determinant of a larger matrix, because for a 3x3 matrix you can just do it this way. But sometimes it actually might even be easier to use cofactor expansion, even on a 3x3, than it is to do the arrow method. So the method number 2, so the arrow method was the first way of doing it. The way cofactor expansion works is that you have to choose any row or any column of the matrix. Now, usually you want to look for a row or a column that has a lot of zeros in it, if there are any. This matrix does have a 0 in the lower right corner, so I would suggest either using the bottom row or the third column to do this expansion. Well, let's just pick the third row. Okay, I'm going to pick the third row. My formula here. So the formula that I've rewritten here, I put it up on the board in class. But what it's basically saying is that as you go across whichever row or column you picked, you're going to multiply the entries of the matrix by the cofactors of that matrix. So, for example, if I choose the third row, I'm going to take, the entries of that row, so negative 4, and I'm going to multiply it by the corresponding cofactor, which is C31, and then plus 1 times the corresponding cofactor, which we still have to calculate, to C32. And then the last term, of course, we don't have to worry about because there's a 0 in front of it. So I just have to find these two cofactors, okay? And what is the 3-1 cofactor? I'll just remind you that what you have to do is find the 3-1 minor. That's obtained by crossing off the row and the column that correspond to that position. and take the determinant of the submatrix that you have after you've crossed off that row or column. This is just a little 2 by 2 matrix. As you can see, we can use the AD minus BC formula for that. And so we'll get negative 3 times 3, which is negative 9, minus 1 times negative 5. So you're subtracting negative 5. In other words, you're adding 5. So that gives you negative 9 plus 5, which is negative 4. So negative 4 is the 3, 1 minor. And remember that, I'm just going to put this right here. Remember that for the cofactors, you have to change the sign on some of the entries. But this position, the 3, 1 position, does not change sign at all. So we just keep the expression as negative 4 times, what did we say? It was negative 4 again for the cofactor there. All right. The next term is a 1. And now I have to do the 3, 2 cofactor. So I'm going to erase what I've been crossing off here. Okay, I'm going to cross this stuff off. The 3, 2 cofactor goes with this position right down here. I'm going to cross off that row and column and take the determinant of the 4 numbers that I see here, right? That's a 2 by 2 block. It's 6 minus negative 5. AD minus BC. 6 minus negative 5 is 11. So I just put an 11 right here. Okay? And remember, though, that that's the 3, 2 minor. I have to change the sign of that because I'm in a negative position here in the matrix. All right? So what do I get for an answer? 16 minus 11, which is 5 again. Okay? You can practice with the same matrix again if you just choose a different row or a different column and cofactor expand a different row or a different column. You should always get 5 as the answer. It doesn't matter which of these methods you use, and it doesn't matter which row or column you choose to expand along in the matrix. Okay, so that's not too bad. Now you can imagine that if the matrix gets bigger, this is going to get harder. Right? Let me show you another example to kind of hit that point home. Suppose that I ask you to find the determinant of the following matrix right here. Okay, I'm going to make a little bit bigger matrix. 3, 6, 8, 1, 9, and then 0, negative 2, 1, 0, 4, and then 0 and 0 and 5, and 2 and 2, and then 0, 0, 0, 1, and negative 1, and then 0, 0, 0, 0, and 2. All right, this is a 5 by 5 matrix. So guys, with a 5 by 5 matrix, when you don't have an arrow method to work with, first of all, and if you choose a row or a column to do cofactor expansion with, you're going to be looking at minors that are 4 by 4. And even for those, you then have to choose rows or columns of each of those to reduce the matrices down to 3 by 3 size. So it's going to be a tedious process normally. The nice thing about this particular example is that there are quite a few zeros in it. So if I was going to cofactor expand this determinant, so for the solution here, I would probably start off by doing row 5 or column 1, either way. Let's look at the 5th row here, right? We're going to have 0 plus 0 plus 0 plus 0, and then finally plus. And notice that this will be a plus position when you're thinking about the cofactor sign changes. That lower entry, that's the 5, 5 position. I plus j, remember that, is just 5 plus 5, which is 10. So this is a positive position. We have a 2 for the entry there, and then we have to multiply it by the corresponding cofactor, which is just the determinant of this 4 by 4 matrix. To find the determinant of this 4 by 4 matrix, I would again start over with a new cofactor expansion along the 4th row, because I again have 0, 0, 0, and a 1. 1 times, here's the 3 by 3 submatrix that you would get if you take this position and cross off that row and column, right? Now you have a 3 by 3 matrix. You can do it again. Expand the bottom row again. You'll get a 5 right there, right? 0 plus 5 times this 2 by 2 matrix. And the determinant of this 2 by 2 matrix is literally just 3 times negative 2. If you just use AD minus BC, or you can cofactor expand it again. But look at what you get. The answer is 2 times 1 times 5 times 3 times negative 2. It is exactly the product of the numbers that are on the main diagonal of the matrix. Okay, so we would get, in this case, we would end up getting negative 60. Turns out that for any triangular matrix, upper or lower, this is an upper triangular matrix, but a nice little theorem is that if A is upper, let's say it's n by n by the way, upper or lower triangular, you have to remember from chapter 2 what that means. It just means that there are zeros in the either below the main diagonal or above the main diagonal. If A is upper or lower triangular, the determinant of the matrix is literally just the product of the entries that go right down the main diagonal of the matrix. That's really, really nice. Okay? So an upper triangular matrix, we don't have to work very hard to find its determinant. We just have to multiply the diagonal entries. So that's what this example is showing. Even though it's a big matrix, we can get its determinant really, really easily. Okay. That kind of leads to an idea for how to find determinants in general. And what the idea is to say, well, even if I have a matrix that's not triangular, maybe I could do some EROs to make it triangular. So that turns out to be a viable strategy. And EROs, you can use those, right? You can use EROs to bring more zeros into your matrix. So if I give you a big matrix that doesn't have any zeros in it at all, and I ask you to find the determinant of that matrix, one of the first things I want you to maybe consider doing is seeing if you can use some EROs to bring some zeros into that matrix, right? Now, you do have to ask a question, though, if you're going to do that, which is, how do EROs affect the determinant of a matrix? Because this could be an issue, right? If we mess up the determinant when we're doing EROs, then maybe we're not going to be so successful with this approach. It turns out that the EROs can change the determinant of the matrix as you're applying them. But they change the determinant in ways that we can keep track of, that we can kind of remember as we go along. So let me give you an idea what I'm talking about. Suppose I have a matrix A, and I just permute 2 of the rows of that matrix to get another matrix B. So I just do one ERO, I permute 2 rows of A. Well, then what will happen is that the determinant of the new matrix B, the determinant of the new matrix B will just pick up a minus sign. So if you permute 2 rows of a matrix, the determinant will pick up a minus sign. You can see that for a 2 by 2 really easily. Like here's a 2 by 2 matrix, the determinant is AB minus BC, right? What would happen if you switched the 2 rows and you did, C, D, and A and B like this? Well, the determinant of this matrix is literally BC minus AD, which is just the negative of the determinant of the original matrix. So when you permute 2 rows of a matrix, the determinant picks up a minus sign. Okay? I want you to remember that. What else could we do? Well, a second ERO would be to start with A and multiply the ith row of A through by a constant K. Remember that one? What does that do to the determinant? Well, it turns out that what will happen there is that the determinant of B will get multiplied through by K. So if you scale a row of a matrix through by a constant, then the determinant of the new matrix gets scaled up by exactly that same factor. Okay, that's for any number k whatsoever. All right. Finally, the third one is really nice. If you do the ERO, where you add a multiple of one row to another, right? This one we use pretty often. It turns out, though, that that particular ERO has no effect at all on the determinant. So the new matrix B will still have the same determinant as the original matrix A. So what you can do, if I hand you a matrix that's not so nice, is you can try and do some EROs to reduce it into a triangular form like this. The triangular matrix has a simple formula for the determinant. You can write that down. And then you can just look at the steps, the EROs that you did along the way, and that'll tell you what the determinant of your original matrix had been. I have another video, the same place where you clicked on the video that you're watching right now. There is another video right in that same area about using EROs to compute determinants. So I'm going to ask you to take a look at that, and you'll see a nice example there of exactly how you can use this information to find the determinant of a matrix by using EROs to simplify it into triangular form first. Okay, so I'm not going to show an example on this video of that, but on my other video that's on my website, right next to where you clicked on this video, you should find something that's labeled with that title about using EROs to find determinants. You should watch it. It'll be helpful to you. I do want to do a quick example, though, to point out something that's a little peculiar that can happen here. Let's suppose that A is a 4 by 4 matrix with the determinant of A. Let's just make something up here. Let's suppose that the determinant of A is 5. Let's ask the question, what is the determinant of 2A? Okay. I'm doing this example because a lot of people sometimes have trouble with this particular property. The popular wrong answer to this is people think that they just take the determinant of A and double it and get 10. But I want you to remember that the matrix 2A is obtained by putting factors of 2 throughout the whole entire matrix, right? It's as if you multiplied each row of the matrix by 2. This second ERO here, this is where you're multiplying one row by k. Every time you multiply one row of a matrix by k, the determinant goes up by a factor of k. But look how many rows this matrix actually has. It has 4 rows. It's a 4 by 4 matrix. It has 4 rows, which means that this factor of 2 is getting applied 4 times, right? Once to each row. That means that the answer to this question is that we start with the original determinant of A, and we pick up 4 factors of 2. So the exponent here is coming from the size of the matrix, and so the answer is actually 80 to this problem. Okay? So I just wanted to point that one out because I've seen people get into trouble with that before, and this way hopefully you guys will be looking out for that. We can think of these first 3 properties of how EROs affect determinant as kind of the start of a list of some properties. There's actually a couple of other properties that I wanted to give you as well. So let me write some more properties right here. So more properties of the determinant of a matrix. Okay, just a few more properties for you to think about. Okay, so maybe I'll just start this as number 4 in my list. Okay, just to kind of continue the list here. The next property, guys, is that the determinant of a transpose of a matrix is the same as the determinant of the matrix itself. So transpose is another operation on a matrix that has no effect at all on the determinant. Okay, so try to start learning these. What about an inverse? Now, not every matrix has an inverse, not every matrix has an inverse, right? And remember that an invertible matrix is one that has a determinant that's not 0, okay? And so not every matrix has an A inverse to talk about, but if A inverse exists, then the formula for the determinant of A inverse is just going to be 1 divided by the determinant of A. You can see that if A was not invertible, you would have a 0 on the bottom here, and that of course would be problematic. So A needs to be invertible for number 5 to make any sense. Another one is that the determinant of a product, if I have A times B, and again, these have to be 2 square matrices that are both of the same size, right? If that's the case, then you can simply multiply the individual determinants together, all right? So determinants respect multiplication, right? So you can find the determinant of a product. You don't necessarily even have to multiply this matrix out. If I give you the product written like this and I ask you what's the determinant of that, well, you can just multiply the individual determinants and get the answer, okay? Let me see. One more thing I want to point out while I'm talking about this. This is not a property of determinants, but you might be wondering about it. Could you take the determinant of A plus B and come up with a formula? The answer is no. There is no nice formula for this. We cannot really say much about the determinant of a sum of 2 matrices. All right? So we have to be a little bit careful about that one. Okay? But going back, I'll go ahead and reiterate one more time. If you have the determinant of, let's say, k times A, and let's say that A is n by n, then this is going to be k to the nth times the determinant of A. Okay, so this is a pretty good list. Just be careful about the addition one. This one does not work well. Addition is not so great for determinants. It's not good for inverses. You can have 2 matrices that are invertible, but you add them together and it's not invertible anymore, right? So plus and minus are not really so nice in the context of some of the material we've been talking about lately with invertible matrices and determinants. But multiplication is good, all right? And powers are good here. Sorry, multiples of a matrix are good. Inverses, transpose, and so on, right? So of course what you could do is you could combine a bunch of this stuff together and try to figure some things out. I've got one in the review packet for the exam where there's transposes, inverses, scalar multiples, and products all mixed together into one kind of bigger problem. Kind of like a theoretical example. I don't have specific matrices in mind, but I could do something like this. Maybe I'll just make one up here. Suppose that the determinant of A, let's say that A is 3 by 3. Let's suppose that that equals 2, and the determinant of B, let's say that B is also 3 by 3. Let's suppose that that determinant is equal to 5, right? Well, so then I could ask you, what is the determinant of, A, B transpose times B inverse squared times 2A, or something like that. I could make an expression like this and ask you to find the formula. Okay, so, well, you would just have to break it down piece by piece. The determinant of A is 2. The determinant of B transpose is the same as the determinant of B by property 4, so that's 5. Okay. The determinant of B inverse using property 5 would be 1 over 5, but I'm squaring that, right? And this is just like multiplying B inverse by itself, so I'm going to multiply 1/5 by itself. And then I've got the 2A. Remember that A is 3 by 3, so I'm going to pick up a 2 cubed times the determinant of A, which is also 2. So whatever that comes out to, I think that's just going to be 32 over 5. That would be the answer. Okay, so you can add, sort of address questions kind of like that if you wanted. Okay. What I want to do with the rest of the video is talk a little bit about what else the determinant is good for. Okay? So we have been learning how to calculate it, but the question is, who cares about the determinant of a matrix? Like, why should we care, right? We learned one thing already. We learned that, you know, A is invertible if and only if the determinant of A is not 0. That's kind of handy. That's kind of a good thing to know. But, you know, what does this number tell us? You know, let's suppose we get a number that's not 0, like 32 over 5 or something. It's like, what does that really mean to us? It turns out that there is a geometric significance to this. So I'm going to give you actually several answers here about why you would care about the determinant. One is it tests a matrix for whether it's invertible or not. The second one is that if A is 2 by 2 or 3 by 3, it has the determinant of A. The determinant of A gives geometric information. And I'm going to tell you what that is, okay? We don't need a lot about this for what we're going to be doing, but it is kind of nice to sort of know this. So in the case of a 2 by 2, so if A is 2 by 2, then if you take the determinant of A, what it does is it measures the area of the parallelogram whose sides are formed by the row vectors of A. Okay? That's a lot of words. When you take the area of any kind of a region, you should always get a positive answer. So in case the determinant would come out to a negative number, which it can, we actually need to take the absolute value in order for this to really make sense. So let me just tell you what this is really saying. I'm going to do it with an example. Suppose that you had something like 1, 5, 4, 1 or something like that. That's a 2 by 2 matrix. If you just look at the 2 rows of that matrix, you can actually make vectors out of this, right? So the first row is just the vector 1, 5. So in the xy plane, I could just draw that vector from the origin up to the point 1, 5. And then the point 4, 1 is over here somewhere, and I could draw that vector as well. And you see, those 2 vectors then determine a parallelogram right here. And what we're saying in this little fact is that the determinant of this 2 by 2 matrix, which you, I'm sure, have already figured out using the AD minus BC formula here, is going to be 1 minus 20, which is negative 19. That number tells us the area of this region. We have to take the absolute value of the answer that we got and give a positive area. And it turns out it's 19. It's exactly 19 units. So for a 2 by 2 matrix, there is an actual significance to this number. You need a little bit of trigonometry, a little bit of kind of Math 250A material, multivariable calculus material to sort of prove that this determinant is telling us that. I'm not going to get into that right here, though. Instead, I want to tell you, even more importantly, really, for us, is going to be the 3 by 3 case. And it's just a slightly more tricky thing. In the case of a 3 by 3 matrix, the significance of the determinant is that it measures the volume of the 3-dimensional object. It's called a parallelepiped. That's determined by all 3 of the rows of A. So it's just like a 1-dimension higher version of this example. So let me just write that.